Hey everybody, Mr. Smith here. Welcome back. What I'm going to do today is to help you tackle one of the truly complicated problem-solving strategies that we can use to work on electric circuits. Why would we do a thing that's complicated? Because in real life, a lot of electrical circuits are actually complicated. Here's an example of one. This is a 100-watt amp from the 1950s. It's built of a lot of components, things you actually understand. So we have a 1 microfarad capacitor. We have a 2200 ohm resistor. We have a diode that allows electricity to only flow in one direction right here. This right here is a variable resistor. A lot of things that can be understood pretty simply. However, when you put them all together, there's a lot going on in a circuit. And what you would do in real life is to use a computer to study this thing. So why Kirchoff's laws? Partly because computers can use the equations that we develop if we use this method, and it can be used to tackle the most brutal questions. So we're going to do some ones that aren't this complicated, but we're going to do ones that you couldn't handle by any other method. So I'll show you an example right here that's actually a really simple one. To start off with, how does Kirchoff's law work? They work because they're based on two fundamental rules of physics. The first rule is conservation of charge. So what the first rule says is if I have a junction, that's point A, also called a node, that if I had 5 electrons go in here and then 3 went out of it, then the other 2 would have had to go on that way. So the sum of the currents entering a junction equals the sum of the currents leaving it. Rule number 1. Rule number 2 is a different way of saying conservation of energy. And what that means is if I follow any closed loop, so if I start at this 6-volt battery, work my way up here, hit that 4-volt battery, go through that 7-ohm resistor and come back, that the sum of all the voltage changes on any closed loop will always have to equal 0, which makes sense. Batteries give energy, resistors lose energy, but charges will always lose all the energy they have to lose between one part of the battery and the other part of the battery at the other end. Okay? So those are the two simple rules, and I'll show you 3 strategies that you can use to employ these 2 rules. Okay, so here we go. The first thing that I like to do in looking at a Kirchoff's law example is get an educated guess about how I think it works. So here's how I do. I dive right in on the closest battery to me. And what I imagine is that this battery pushes in this direction. And I go to the first node that I see, which is right down here in letter B, and I just follow the direction. And I go this way, and then I ask myself, does the direction of the arrow that I'm writing right now make sense? And to me, the answer is yeah, because I see a 6-volt battery pushing this way. Charges would want to run this way. Oh wait, 4-volt battery also pushing in this direction? Yeah, I actually feel pretty good that charges will flow up, they're going to hit point A, and they're going to circulate back to the battery, and that gives me a feeling that I have understood how this left-hand loop of the circuit's going to operate. Here's the thing. You're allowed to be totally wrong. I'll show you why later. But I think I'm right. I'll do the same exact thing with the second loop. So I'll just go to the next battery and I'll follow the smallest loop I can find. So 8 volts is going to push this way. Charges are going to hit this node and they're going to fly up this way. Yes, again, helped along by the 4-volt battery. And I think that this current is going to flow here. Okay? So that gives me a feeling that I've understood how this circuit is going to work. I'll talk more about why that's important in the next slide. You might notice, if you've been paying attention, that there were I's, letter I1, I3, and I2 already written on this circuit. So I took this example from a physics book called Shom's Outline, where they already gave me suggestions for how the currents would work. The thing is, I didn't like their suggestions. I like to do step 1 because I always want to make sure as I think about the circuit that I don't end up in conflict about how a shared leg of the circuit will work. So what do I mean is this left-hand piece of the circuit right here shares this part of the circuit in common with this one, right? So what I want to make sure is as I visualize this, it made sense to me that this first loop over here was flowing counterclockwise and the current in this part was flowing up. Same thing, that idea was reinforced over here. That made me feel good because I didn't want to have 2 contradictory ideas about how this one shared leg works, okay? That's subtle point number 1. Subtle point number 2, and then I'm going to get to this guy right here, is that what we're going to call I1, I2, and I3 have everything to do with how the circuit breaks apart. So a node is a junction. A and B are both nodes. And what I want you to imagine is unsnapping A and B and pulling the pieces of the circuit apart. So what have I got? Everything that moves to the left is I1. You can see this leg down here, this leg over here on the very left, this leg on the top. All of that is going to be current 1. This is a different part of the circuit. It could carry a different current than this one, and so that is what we called I3. I2 was this piece on the right. Okay? So now that I feel like I've understood the circuit from my first discussion, put my little arrows back in, I'm going to write the node equation. It's real easy. I3 looks like it flows up into point A. Because this left-hand loop works counterclockwise, what happens is I1 moves that way out of point A. Because in the right-hand loop, I2 moves to the right of point A, I've got now all the three elements that I needed. I've got I3 coming in, I1 and I2 going out, and how do you write conservation of charge? I3 went in equals I1 and I2 coming out. Boom, done. That's as simple as that. Okay? Node equation, usually pretty easy to get. Now, loop equations. In real life, I'm going to write two loops. I'm going to write an equation for this loop. I'm going to write an equation for this loop. There was a third loop that was possible around the outside, and if I have time, I'll talk about it. But what I'm going to start is go to the next slide and write an equation that uses conservation of energy. So what do? Is I'm going to walk around counterclockwise on this loop, and I always start with a battery. So what does a battery do? It gives me energy. So I have positive 6 volts. What happens here? A charge hits B, migrates up, it hits this 4-volt battery. Ooh, 4-volt battery. Because I was moving in the direction of the battery's push, it gave me a bump. So I put +4. What happens here? Charges hit A, and they go then this way. Now I'm in I1 territory, and what happens is there's a voltage drop. So I know the resistor, I know the current through him, and I'll just now write down -7I1 equals 0, because the sum of all the voltage drops around a closed loop equals 0. Okay? Now, this is why this example that I'm doing right now for you is crazy easy. It's just that the math falls apart so simply. What I'm going to actually have here is a situation that almost never happens. I'm actually able to solve for one of the currents right away. So I've got 10 minus 7I1 equals 0, and what that tells me is I1 equals 10 over 7, and that's 1.43 amps. So that's just awesome and sweet. Let's go to the next equation and see what we get from that one. So in this right-hand loop, I've got 8 volts, and I'm going to move to the left. Okay, so charge came out of the 8-volt battery. Great. Hit B, moved up. Oh, got another bump. I was moving along the circuit in the direction of the 4-volt battery, so I get +4. Fantastic. What happens? Charges hit A, and they migrate through this guy. We did this exact same thing before. Charges are going to lose energy on that. How much? -5I2, right? Because I'm on the second leg of that circuit, equals 0. So sum of all the voltage changes adds up to 0. So 12 volts equals 5 times I2. And again, this one's so simple. It just falls apart for us and gives us the answers we were looking for. And then we can wrap this whole thing up on the next slide. What does wrapping it up look like? If you get the currents in each of the legs, there's nothing you can't do. And usually the problem ends there. They might ask you what's the voltage drop on the 7 ohm resistor, but you could easily figure it out. So what have I got? I've got that I1 we already solved for as 1.43 amps. We had that I2 was equal to 2.4 amps. And how are we going to get I3? Well, I had my other equation, right? I3 equaled I1 plus I2. And I can just go ahead and add those up, and I get, not 2, but rather 3.83 amps. Done. End of story. Okay, so I'm going to make this snappy to fit this in hopefully under the 12-minute mark. Ready? There's a subtle point that I want you to get here. If I start at the 6-volt battery, I'm going to write it a loop equation, and I'm going to walk around the outside loop, and there's something that's really important that you're going to see. If I start walking along the 6-volt, out of the 6-volt battery, remember this loop worked counterclockwise, this loop worked clockwise. What I'm going to do as I walk along the big loop is the next thing I'm going to encounter is the 8-volt battery. Well, here's the story. I'm now flowing my charge across the 8-volt battery in the opposite direction from the way it likes to go. So what's going to happen? First thing you're going to learn from this extra example here, that's going to steal energy from my charge. I'm flowing across a battery the wrong way, I lose energy. Okay? What's going to happen next? Well, my charge progresses from there. Notice now that I'm moving again against the way that I thought the current was going to go. I thought I2 was going to go down in this circuit because it worked clockwise. That's okay. All it means is I'm allowed to be wrong. Just remember what you did. Because I'm flowing against the way that I thought, as I traipse around this part of the circuit, that voltage change here isn't going to be a voltage drop. It's going to be a +5 I2. Not a -5, a +5. Then what's going to happen? I'm going to hit the 7. Okay, now the charge is moving the way I thought the current would work. So a charge will lose voltage normally on a resistor. I'm going to go -7 I1. And then there's nothing else before I get down to the battery. I'm done. That's my equation. What I want you to do is plug in the numbers that we actually got and see if this works. All right, so thanks for watching. Bring your questions to class. Be talking with you soon. Take care. Bye-bye.